Mingione. He's a well-known mathematician. It's very well known for his results in regularity theory. And I have known him for the last 10 years, studying his papers, and I take the opportunity to thank him personally, because at the beginning of my career, he was very, was helping me a lot, and we chat. It was the time that before pandemic, chatting like through Zoom didn't exist. So I think we used Skype, and I learned a lot from him, and I still do. I still read his papers quite often. And so with no further ado, I pass the floor to Rosario. Thank you so much. You will see that he, on the top of being an excellent mathematician, he's also an excellent speaker. So we are in for a treat. So with no further ado, Rosario, the floor is yours.
Okay, thank you very much, Eduardo. So it's, I think the last time you chaired a talk of mine was in Rio de Janeiro. And now I didn't expect that you were chairing a talk of mine in Parma. So let me, so should I share the screen right now, right? I mean,
yes.
Okay, I share, now I can share the screen. Tools, view, enter full screen. Is that okay now?
Perfect.
Okay, perfect. Now we can finally start. Okay, so thanks a lot. And okay, non-uniformly elliptic problems. Okay, this is a series of talks that I'm going to give every time I present some old results and some more new ones. So next month there will be more new ones, and in 2 months there will be more new ones. But it's a continuous stream of talks and things that I'm putting in and out from the same talks. Okay, let me give you just a flavor of what I'm going to talk about. So I'm mainly focusing on the variational case. So I'm going to consider integral functionals of the calculus of variations of this type. And the idea is that I want to analyze the regularity of minimizers in strict connection to the regularity of the so-called external ingredients. So the dependence on coefficients and the external data F. So the idea is that we want to find the minimal. So the idea is that we drop X, we drop F, and then we assume that, let's say, that the functional has Lipschitz minimizers. And then we want to know what are the minimal assumptions we have to put on X and on F in order to get that the minimizers are Lipschitz continuous. So the idea is that we want to get really the minimal assumptions on the external ingredients in order to get that minimizers are locally Lipschitz. So in the uniformly elliptic case, so just let me give you an example. Consider the classical problem of the P growth functional. And so you minimize dv to the P, and then you add coefficients, let's say C of X as a coefficient, and then a data F of X. And then you want to find the minimal assumptions on C and F in order to guarantee that minimizers are still Lipschitz, for instance, but then also more regular beyond Lipschitz. But let's start with Lipschitz. So the gradient is bounded. Okay, this has been solved in this case, but also in more general cases, has been solved by Tuomo Kuusi and myself a few years ago, where we actually gave a positive reply, a positive answer to an old conjecture of Uraltseva. And the conjecture of Uraltseva stated that if you take the P Laplacian operator, then the condition you have to put on F, and eventually we also added C of X, in order to get that the gradient is bounded, is independent of P. And this is actually the outcome, because whatever P is, it is sufficient that Cx is Dini continuous and F belongs to the Lorentz space as a Ln1, and then the U is continuous. And actually, you can replace the P Laplacian operator with any other quasi-linear operator with the same type of growth condition, according to Lagichenska and Uraltseva assumptions. So this is a final theorem that tells you what are the best assumptions. And let me just recall you what is the Lorentz space Ln1. because it will appear again several times during the talk. So this is essentially the largest space the gradient can be prescribed to belong to in order to get an extension of the Sobolev-Moro embedding theorem. So you know that if the gradient belongs to Ln plus something, then you know that this Hilder continuous. And then when this plus something goes to 0, you go to Ln, but Ln is not sufficient but to get VMO continuity. Then you have to stop a bit before, and then this bit before is given by the Lorentz space Ln1 that says that G belongs to Ln1 if the level sets decay fast enough in order to make this integral converge. So essentially, the second index that times the first one serves to encode logs after the powers. So that's the Lorentz space. So behind this definition, there is something very natural. That is, the next thing you want to consider after powers are the logs, and then the logs are encoded by the second index, and that's it. Okay, so what do we mean by uniform ellipticity? If we get fz like z to the p, that is the case of the p Laplacian before, then uniform ellipticity is measured in the following sense. You take the Hessian of f, okay? So the Hessian has the highest and the lowest eigenvalue. And by ellipticity, these eigenvalues are always positive. So the ratio between the highest and the lowest eigenvalue, it's usually a constant that intervenes in all regularity estimates. If this constant is bounded, whatever z is, then you have a uniformly elliptic operator. So this is and in the case of the P Laplacian operator, that's what you get. Okay. Of course, the non-uniform ellipticity means that the ratio that we call the the ellipticity ratio goes to plus infinity when z goes to plus infinity. So when the previous condition is not satisfied, then you get non-uniform ellipticity. And this is a very classical topic. It's a very classical. So you lose the control on this ratio that intervenes in all regularity estimates. And losing this control, then you are led to check out this ratio might blow up when the gradient goes to when the gradient goes to plus infinity. So there's a competition occurring here. The gradient tends to go to plus infinity. You want to bound it, but in order to bound it, you have to use that this ratio is bounded, but this ratio is not bounded, and therefore there's a competition between the two. Okay, this is a very classical topic, and in this talk, a main source of examples is given by when you have the so-called polynomial non-uniform ellipticity. That is, this ratio might blow up as a power of the gradient. This is one of the most classical things that you have also, for instance, in minimal surface equation. That's what it happens. And this also happens when you get a PQ growth functional, because there are some certain functionals that grows like P from below and from above, and they usually couple with the similar growth conditions on the Hessian, that is on the second derivatives, and therefore the ratio grows like z to the q minus p. These are so-called PQ growth conditions and describe a general situation where polynomial non-uniform ellipticity occurs. Okay, this is a very classical topic, and classical studies have been done by Lagushinsky and Duraltseva. There's a classical book by Neil Tudinger, Leon Simon, and many people over the years, and especially these PQ growth conditions have been treated extensively in a series of pioneering papers by Marcellini. Okay, examples. You have, for instance, a functional when you are not only penalizing the whole gradient, the full gradient, but you're penalizing each directional derivative with its own power. And therefore, you get that usual non-uniform ellipticity conditions are not satisfied, and the ratio goes like z to the highest power minus the smallest power. So this is a classical example. Another classical example, you take an Orlich function that continuously oscillates its growth, still being convex. You can cook up the parameters in order to get them still convex. So so you see, when t goes to plus infinity, sign goes between -1 and 1. So this has 3 from below and 5 from above. And the fact that you get a log-log, then you have these oscillations slow enough to guarantee that your integrand is still convex. It has been considered by several people like Talenti and other Chunky and other people. Okay, and then you can get very fast growth conditions. You can combine several exponential functionals, several exponential growth conditions. And then you go far from the realm of polynomial non-uniform ellipticity. You don't have a polynomial non-uniform ellipticity, but an exponential one. This has been first considered by Duke and Els in the setting of harmonic mappings, then by Liebem and Marcellini and Evans in the setting of weak KAM theory in order to get a different approximation of the infinity Laplacian. Okay, now the point is the following. A general paradigm is the following. We have seen that the ellipticity ratio in the case of functionals with PQ growth grows like q minus z to the q minus p. So if you remember that we were talking about an initial competition, the gradient, which tends to be unbounded and therefore makes the ratio, the ratio blowing up with a certain speed. But then if the ratio is blowing up with a certain speed, then it's more difficult to prove that the gradient is bounded. Then the idea is that if the two eigenvalues, they grow too much differently from each other, then regularity is lost. And in fact, there are a few, by now classical examples by Marcellini and Giaquinta that states that a necessary and sufficient condition in order to get that minimizers are irregular is that this ratio between the highest and the slowest growth cannot be too large. And in fact, it cannot differ too much from one, depending on a quantity that varies with n. And this is a classical example of Marcellini and Giaquinta. So in fact, if Q and P are too far, minimizers can be even unbounded. So you get convex functionals, perfectly convex functionals with analytic ingredients, but still minimizers are unbounded. So therefore, it's the real difference between these eigenvalues that it's occurring in regularity. Okay, a model positive result is given is the following one, which was one of the first results appeared in this generality, and it's not this is not the most general result. It's a tutorial result in the sense that it shows in a very good way what is going on in this setting. Now you get a convex integrand whose the smallest eigenvalue is not smaller than z to the p minus 2. And the highest eigenvalue is not larger than z to the q minus 2. And therefore, the ratio grows when z is large, like z to the q minus p. And therefore, if you have this bound, then minimizers are locally Lipschitz. So minimizers are locally Lipschitz, and you can immediately see that when p is equal to q, for instance, if you take the case of the p Laplacian, this is the classical L infinity LP reverse inequality, typical of harmonic functions. Otherwise, you don't get an homogeneous inequality. You get an inequality that reflects the non-isotropicity of the problem. So the idea now is that if q is close to p enough, then it's okay, then you're in the game. Otherwise, you're not in the game. And then, of course, once you discover this condition, usually all the bounds I know are of the form 1 plus something that goes like 1 over n. And then, of course, you might speculate what is the best bound, which is actually unknown, still unknown for the gradient, for this kind of theorem. You know that this bound is sufficient, but you don't know what is the best one. In fact, there have been several interesting papers by, for instance, Bella and Schaffner, who cooked up an interesting method of choosing test functions adapted to the problem to improve the bound from n to n minus 1. In fact, they they ultimately reduce to apply Sobolev embedding theorem not on in space but on surfaces. Then there's another related paper, interesting one by Schaffner, who also applies to partial regularity. This paper I like very much because under this condition and no convexity assumptions, you don't look at the gradient regularity, but you look at the L infinity of minimizers, and then you get the sharp bound. This is sharp. And then there's another interesting paper by De Filippis, Christensen, and Koch, which is in preparation, where they get another bound under special assumptions. Okay, but this is just to give an overview of what's going on around these bounds. Okay, when minimizers are bounded, then there are certain hidden interpolation effects for allowing you to get a non-dimensional bound. So for instance, Q less than P plus 1, it's sufficient. This was first noticed by Ryaltsev and Udaletov in a very pioneering paper from '84. And then it has been extended over and over by several authors. I just mentioned a few. But this is just to tell you that if you start from, this is a general fact, if you start from a better minimizer, then you can relax the bound. And we will come back on this later. Okay, now let me go back to this problem. Let me go back to this problem. Up to now, you saw that I showed you a few results on perfectly autonomous functionals. Therefore, functionals that are not depending on external ingredients like x or like forcing term f, but they are just perfectly autonomous. And now we want to upgrade this, adding coefficients and ingredients. And the problem is the same. Can we do the same things in the non-uniformly elliptic setting? So in the uniformly elliptic one, we saw that the dependence on x must be Dini continuous, and f must belong to ln1. So we will see that only part of this is true in the non-uniformly elliptic case. Okay, the very interesting thing is that still in the new, okay, the general philosophy of what is going on here is that as far as the right-hand side is concerned, f still has to belong to ln1, so you do not have to worsen this requirement. Because this requirement is a structural fact that only depends on the fact that the Euler-Lagrange equation is of divergence 4. So you have divergence of a vector field equal to f. So commute the divergence with the gradient, and then by the Stein's theorem, you will get that the right-hand side must always belong to ln1. On the contrary, the degree of regularity that is required on x is not the same and depends on the non-uniform ellipticity of the operator. And this is due to the basic fact that Schauder estimates fail in general in the non-uniformly elliptic setting. So they are not always true. I'll show you a few examples later on. But let me first consider the first requirement. So let me start, therefore, from a weak non-autonomous case, that is, the x is not coupled with the gradient, just appears an external data like f. And therefore, let me be in perfect generality, and therefore I bound from below the lowest eigenvalue by G1 and from above by G2. So G1 and G2, they play the role of the lowest and the highest eigenvalue. And the basic assumption I'm going to put is that the ellipticity ratio, which is bounded by G2 over G1, can be controlled as a power. H is a power function whose shape I'm not going to describe to be faster, but let me tell you in advance that all these results then turn out to be sharp. It's of this quantity, which is exactly the full energy that the functional can control from below. For instance, in the P Laplacian case, G1 is z to the p minus 2. If you multiply by s, then you get s to the p minus 1. If you further integrate, you get z to the p. So that's the growth of the function. So that's the quantity, the largest quantity, the function, the integrand f can control in terms of coercivity. Okay, and under this assumption, we are able essentially to prove the same theorem. So whenever you get a non-uniform elliptic operator with functional, with this assumption, then the right-hand side, the property is invariant. So if f belongs to Ln1, then the gradient is bounded. And you have this apparently weird estimate. You can control the L infinity norm of the gradient when you put here with this quantity. This is actually not strange because in the P Laplacian case, the whole left-hand side reduces to du to the p in L infinity norm. This is true both in the scalar case and in the vectorial case when you add the so-called quasi-diagonal or Uhlenbeck structure. So this tells you that this Lorentz space condition is really a universal property that doesn't change when you change the operator. So this is a so-called very general version of Ural-Sevas conjecture. That is, the right-hand side is totally independent of the operator whenever it is uniformly or non-uniformly elliptic operator. So it's a totally independent factor. So we got this result injecting in this kind of approach a nonlinear potential theoretic methods that we developed with Tuomo Kuusi a lot, for instance, in the setting of nonlinear potential theory. So we put some ingredients from nonlinear potential theory in this new setting. And this is something that I've been learning at the beginning from the Finnish school when I was there. And then I injected this in non-uniformly elliptic problems, and this was not done before. And the technique, essentially, it's a linearization technique that allows ultimately to reduce not only non-uniformly elliptic operators to uniformly elliptic one, but even to the Laplacian. It's in a sense a bit brutal, but it works. And it covers all the previous general results from the theory. It gets also local estimates of some results of Chunky and Maziab that in the classical uniformly elliptic case. And it recovers in the non-uniformly elliptic one where f is equal to 0, the classical theory of Marcellini plus a few improvements. So it is sharp in this respect. And it also recovers the Orlitz space setting. Okay, for instance, if you start from this very weird estimate and you make it particular, for instance, to the PQ case, to the functional where you have P and Q growth with the eigenvalues, you get this one. And if P is equal to Q, you get the standard estimate in the P Laplacian case. So this apparently weird estimate gives you back, when you apply to particular cases, the usual estimates. So you get the classical L infinity LP estimates for harmonic functions, but you also get the classical estimates of Marcellini and so forth. So it's a sort of general estimates, which is bound to work in any case. But then when you apply to special cases, then you get familiar things back. Okay. It also works in the case when you get any composition of the exponential. And so if you get any composition of the exponential, and this is a particularly difficult, technically speaking, to handle, then you still get that the right-hand side should be in Ln1, and this is okay. So from a theoretical viewpoint, it should be easier to deal with this functional because you're penalizing a higher and higher growth of the gradient. So it becomes more and more difficult to break Lipschitz continuity, still fixing minimality because you're penalizing a very large energy. But in fact, it is not so easy, and it is much more difficult than in the polynomial case because this doesn't satisfy the delta 2 condition. So you cannot manipulate constants without breaking integrability, essentially. So all the classical tools they fail in this setting. Okay, so Up to now, we have clarified what happens when we have the right-hand side, f. So when we have a right-hand side, nothing changes between the uniformly, by passing from uniformly and non-uniformly elliptic setting. It is very much okay. Because essentially, the idea is that you have a divergence of a vector field, which is the variation of the functional equal to a beta. And therefore, whatever is under the sign of the divergence, then the divergence can be traded and treated as a gradient, and then you can apply Stein's theorem in a way. It's like applying Stein's theorem, commuting divergence with a gradient. Of course, behind this commuting, there's a whole theory of singular integrals that doesn't hold in a nonlinear case. And the idea is that to reproduce from behind this ellipticity property, using the ellipticity properties to reproduce this property of singular integrals. Okay, but now we want to analyze what happens if you add coefficients. Now we have seen that nothing changes if you add the right-hand side, but now it is very different when you add coefficients. So according to classical Schauder's theorem that still holds in the non-uniformly in the nonlinear case, but uniformly elliptic case, then Haney-Hilder continuous coefficient should work, and even Dini continuity should work. It is not the case here. It is not the case. And because the degree of regularity you have to assume on this partial function depends on the growth of this. So there's a subtle interplay between the regularity you have to require with respect to x and the growth assumptions you have to require with respect to z. And there are old results that I first proved with Esposito and Leonetti, and then with Fonseca and Malia in a more extended form, and tells you the following. Consider this functional, which is scalar, convex, and with Hilder continuous coefficients. Take alpha between 0 and 1, to be simple. Okay, you can also make it analytic with respect to the gradient variable. You can put 1 plus dv squared to the q minus b, but let's consider, so it's, you can build up a convex, scalar, and analytic functional with respect to the gradient variable with Hilder continuous coefficients. So Schauder theory should apply here, but this is not the case, because if P and Q are far enough depending on the regularity of the coefficient, then you can find a minimizer whose set of essential discontinuity points, that is no Lebesgue points ultimately, is as large as the set of any other competitor. So this is a striking example of the fact that you lose any kind of regularity, also treating a convex, scalar, and smooth functional. And this is due to the fact that it has no standard growth conditions in a way we will see later on. And you may, of course, wonder if this condition is sharp or not, and it is, because in fact, this counterexample shows that the next theorem is sharp. So in a series of papers starting with Maria Colombo and then with Paolo Baroni, we treated the regularity of minimizers of this functional. So it's a double phase functional, because when a of x is 0, this grows like, when a of x is 0, this grows like dv to the p. Otherwise, when a of x is larger than 0, it grows like dv to the q. So it switches between two kind of ellipticity rates. Okay, if you get a minimizer, and if you assume that q over p is less than or equal than 1 plus alpha over n, then the gradient is Hilder continuous. And this is sharp if you look at the previous example. If you start from a bounded minimizer, then you can relax the previous bound in the following one. And this is still sharp, because in the counterexample before, we fix the boundary, bounded boundary data. So the minimizer is bounded, but yet discontinuous. And the difference between Q and P is at least alpha, as prescribed here. Moreover, the more regularity you start with on the minimizer, the more you can relax the bound. So for instance, if U is C0 gamma, then the bound relaxes in this one. And this shows the optimal, I mean, the asymptotic you expect on gamma. Why? Because when formally gamma is 1, this is plus infinity. So there is no bound. But when gamma is 1, this means that the gradient is bounded. So it's irrelevant if the functional is uniform or non-uniform elliptic, because the growth at infinity is not seen anymore by the minimizer, because the minimizer has already a bounded gradient. So what happens when the gradient is large is irrelevant. And this reflects in the fact that no bound is required. So there's a new phenomenon here, that is Schauder theory holds for this functional, provided the ellipticity ratio doesn't grow so fast. Okay, this result, the sharpness of this bound, as I told you, is in this paper by with this paper with Esposito and Leonetti, and then the sharpness of the same bound is in the same counterexample. And then this sharpness of the condition is in a very interesting recent paper by Balchi, Diening, and Surinachov. There's also a recent paper by Balchi and Surinachov on a limiting case of this functional. It's a recent paper on nonlinear analysis, and it's a very interesting one. Okay, let me show you why this condition. Okay, now if you look at this functional, what is the point? The point is that consider that A is a constant. Okay, this functional is uniformly elliptic. So if there is no dependence on x, or if you freeze x, this functional is uniformly elliptic. You can compute, because it's like z to the p plus z to the q. And this is perfectly uniformly elliptic because it bounds the same eigenvalues from below and from above. So the ratio, it's bounded exactly as in the P-Laplacian case. So here the whole game happens according to this phase transition around the zero set of A of x. So therefore, you have to consider a different quantity to measure the non-uniform ellipticity because before you fix x and you consider the sup, the ratio between the highest and the lowest eigenvalue. Here you fix a ball and you consider the sup of the highest eigenvalues over the inf. And then you compute that in a ball where A of x touches 0, which is the interesting set, A of x is Hilder, so it has to decay, it's like r to the alpha. So this ratio is like du to the q minus p times r to the alpha. And then you perfectly see what's the game here. The difference between q and p tends to make things blow up, while r to the alpha tends to correct things because tends to keep things bounded. And therefore, the highest alpha is the highest is q minus p, allow it to be. So this is a particularly suggestive capacitary explanation. Let me consider again this functional. And this is like a P-Laplacian times another piece. So apparently you might consider two different capacities connected to this functional. The first capacity, and now we are fully in Finnish territory because these are things that you can find in the school of Olli Martio, people like Heinonen, Kirpelainen, Lindqvist studied these things in detail. So you get the P capacity that controls the first piece. For the second piece, you get another capacity. For instance, take the special example of A of x equals to x to the alpha. Then you get a different weighted capacity. This capacity is not exotic. It's been considered several times in the literature. It is treated, for instance, in the book of Mazias, Sobolev spaces. I mean, it's a weighted capacity. Okay, this capacity grows like r to the n minus p, the first one. The second grows like r to the n minus q, and then you have to add this killing term that tends to kill the energy. The capacity measures the energy you spend from going from 1 to 0 in a small set. But if you have a coefficient, then the energy decreases. So the energy increases with p, but decreases with alpha. Now, if you look at all these connected things like regularity of minimizers, removability of singularity, and so forth, all these things are ruled by capacities. Now you have two capacities for these kinds of functionals. And you might like to think that if the two capacities do not connect to each other, then you might create singularities. And that's how the example is constructed, because there are certain sets you can see with a part of the energy, while there are other sets you don't see with the energy. So if you want to have regularity, if the two capacities have to connect to each other. And in particular, the second, which is the highest, the largest one, because it has a largest growth with respect to the energy, should be controlled by the first. Now let's impose this condition that this quantity is controlled by this one, and you get exactly the bound. So this is a capacitary condition. So whenever you have this condition, then you consider these kinds of functionals, and then the capacity is controlled by the other. The two capacities match, and therefore you get a nice thing, something which is treatable, that works. I mean, and this has been considered at length also in a series of papers by De Filippis and Klebitska, and also Klebitska and Karpingen. And there are these anisotropic capacities, but it's a different story. Okay, so what we have learned up to now is that when you switch to the non-uniformly elliptic setting, then you go to this new range. So there is sensitivity on coefficients. Okay, so therefore, the quantity that we have learned is important is now a larger quantity that detects more non-uniform ellipticity. So it's a non-local ellipticity ratio, that it's the sup between the sup of the eigenvalues when x varies. Okay, and now I'm going to present some joint results with the Cristiana De Filippis. And we consider now the Fully case in the vectorial case. So we consider functionals of this type where there is an extra x dependence attached to the gradient. And therefore, we describe the lowest eigenvalue and the highest eigenvalue with two different growth functions as before, but now these growth functions are supposed to depend on x2, because we want to consider an extended ellipticity ratio. And of course, since the regularity with respect to x is important, we shall prescribe that you have differentiability, but not Lipschitz continuity of coefficients. We shall use an approach introduced by Marcellini, Eleuteri, and Mascolo, but also previously in the literature by Christensen and myself in the uniformly elliptic case, that we consider Sobolev coefficients. So we prescribe that coefficients grows like LD function. So in the usual Lipschitz setting, H should be L infinity. Here is just in LD with D larger than N. And then we want to reformulate the previous conditions. So these conditions are technical, but all of them lead to sharp results. So these conditions look technical, and they must be because they are bound to catch all possible examples. Then when you apply these conditions to concrete special cases, then you will get sharp conditions and readable conditions. So I'm sorry for these technicalities, but the point is that these conditions are bound to catch all possible cases. So as before, we introduced the coercivity function, which is the growth with respect, which is regulated with respect to the lowest eigenvalue. we bound the ratio between the two eigenvalues by a power function, and this is exactly as before. And in addition, we introduce a variability condition with respect to the x dependence. These conditions are technical, but as soon as you drop one of them, all these results fails. All the results fail. So, in fact, one of the strengths of this paper is that we find these general conditions that, in all possible respect, they reduce to be minimal when you switch to examples. So, once you have this, then we are able to prove this anisotropic intrinsic estimate for the gradient. So we do consider the L infinity norm of the coercivity function, which is this one, composed with the gradient. And then we can bound essentially with the functional, and we have the same assumption in Ln1. And of course, the game is always the same. Now we take this meta theorem and we make applications to particular cases. For instance, in the case of PQ growth functional, we prescribe that coefficients belong to the Sobolev spaces W1D. So coefficients are not Lipschitz, but by Sobolev-Morey embedding theorem, they are Hilbert continuous. So in particular, if you consider this special functional, we assume that coefficients are not Lipschitz, but are differentiable and belongs to W1D. This is and this is when f is equal to 0, this is a theorem of Eleuteri-Marcellini and Mascolo. So we catch this special case. So you see, this is a different way to say that coefficients are Hilbert continuous. And now what about the optimality? Well, this is the optimality essentially. If you consider that under this condition, if f belongs to Ln1, and if this bound is satisfied, then the U is locally bounded. So the previous Eckward theorem reduces to something which is very easy to handle. Is this bound optimal? The answer is yes, because we know that C of x is in W1D. So if C of x is in W1D and D is larger than N, then C of x is Hilbert. So this can be rewritten in the following way. And the bound, if you apply this to the double phase functional, it gives you the perfect bound. So in a way, this is the sharp differentiable version that via embedding gives you the optimal Hilbert continuity beyond which you produce counterexamples. So in other words, the first theorem tells you that if you analyze this functional, then you get a PQ growth, a non-uniformly elliptic integrand, an optimal Ln1 function, and an optimal Sobolev coefficient. And then you get Lipschitz minimizers, and you can get better than that in this generality with this optimal bound. But this is the difference. You don't really have to keep in mind always all these times this functional. This just tells you that this is optimal in this setting. So if you apply this to the double phase functional, then in the double phase functional you get that A of x must belongs to W1D, and therefore it's C0 alpha, and therefore the bound should be this one, and it is in fact this one. So in this bound you see the previous one with the double phase via Sobolev-Morey embedding. So you read the previous bound in the following way. Okay, this is an application to polynomial non-uniform ellipticity, but you can also apply this to exponential growth cases, and this is very, very delicate because there's a lack of delta 2 condition. So whenever you move a bit the coefficient, integrability is lost, because the integrand does not satisfy delta 2 condition. This means that if you have a function such that x of f is integrable, x of 2f is not integrable. So you have to be very, very careful in this treatment, but still you get this result, which is even better than before. Because before we saw that you have to take D large enough, so the differentiability, the integrability rate large enough to compensate the distance between P and Q. In the case of exponential growth functional, any D is sufficient. So any rate of micro-Hilbert continuity is sufficient to get the result in the exponential case. So this is very counterintuitive. So you require less when non-uniform ellipticity gets stronger. And in fact, it is not really so. Because when you deal with exponential functionals, then the ratio of non-uniform ellipticity becomes comparable to the functional itself. And therefore, you magically require less. This is a very counterintuitive fact. And it's somehow striking that any rate of micro-Hilbert continuity is sufficient to get here. So the exponential functionals behaves better than the polynomial functions. And this is another sign of the fact that you are minimizing a much stronger norm, although it's more difficult to handle technically. So at the end, you get a counterintuitive, but then after all, intuitive result. You are minimizing a functional that grows more and you require less on coefficients. And this can be adopted in any kind of generality. You can make a variable exponent inside. You can put any composition of exponentials. You can put coefficients everywhere. The condition is invariant. So any minimal Hilbert continuity gets you the local Lipschitz continuity. So in this paper with De Filippis, we have really a general approach to cover all the possible cases. And in particular, we can use this approach to go back to standard uniformly elliptic functionals or equations. These have been treated at length by, for instance, Lieberman, Cianchi, and Mazia. And therefore, we can consider uniformly elliptic operator. So we go back to the classics, and we apply these techniques here, and we see what we come up with. And this prescribes uniform ellipticity. And then the result that we have, so these conditions imply uniform ellipticity in the sense that the ellipticity ratio is bounded by this fixed constant. But this is just a computation. So trust me, this is uniformly elliptic. And then you can get this result, which is new even in the P Laplacian case. So this is an alternative formulation. You know that if you put coefficients, then these coefficients must be Dini continuous. If they are continuous but not Dini continuous, then the gradient is not bounded. This is a counterexample of Mazia, Van Schaftingen, and Xin, I guess. And so Dini continuity is required. This is a standard in elliptic theory. Here we find, for the first time, an alternative approach. We trade the continuity with the differentiability, and we prescribe that the gradient is in ln1, exactly as the data. And then this still implies that U is locally bounded. Observe that by Stein's theorem, if the gradient is in ln1, then C of x is continuous, but not in general Dini continuous. So we find for the first time an example, a new criterion to get that the gradient is bounded that goes beyond the standard Dini continuity. Because the idea in all this regularity theory is that you have to iterate constructing dyadic decay, and Dini continuity therefore is important. Here you don't use dyadic decay, you use the differentiability, and you just have continuity. So this is new in particular when A tilde is due to the P minus 2, that is the case of the P Laplace. We can apply this to obstacle problems, and we get the sharp condition on obstacle problems. And this is new, again, even for the P Laplace. If you are minimizing the functional with the lower obstacle, and the second derivative belongs to ln1, then the gradient is continuous. Again, usually to get this result, you need that the gradient of the obstacle, p phi, is Hilbert continuous. Here we do not require that it is Hilbert continuous, but it is just continuous by embedding. So as far as I know, this is for the first time that you get a non-Hilbert gradient obstacle such that the gradient is bounded. And this is optimal in this generality. This is new already for the P Laplacian, but it's for the first time with any obstacle for the exponential or for all these kinds of most brutal functions. And this is an application of the same technique. In another paper with always with Cristiana De Filippis, we can also treat, just as an announcement, with the functionals that have these kinds of structures. So you are with nearly linear growth conditions and you're approaching minimal surface things. And it's again the same story. So this is the nearly linear growth case. This is the nearly linear growth case. And finally, if there's time enough, is there time enough, or we already? Eduardo, what do you think? 5 minutes more, or?
Yeah, sure. Yeah, please.
Okay, just 5 minutes more. I mean,
5 more minutes.
Let me go back to the to a previous theorem. If you get this double phase functional, we have seen that the bound improves if you start with higher regularity. So the higher regularity of minimizer you start with, and then the better bound it gets. Okay, this is for this special case. And now, in a recent paper, it's in a special collection dedicated to Vladimir Mazia for his 18th birthday. We proved that the same thing holds in general with the same asymptotic for any functional in the vectorial case. So we take a functional of this type in the vectorial case, and we wonder when a minimizer that is by minimality in W1P is in the better space W1Q, because this is the first step of regularization beyond which you can start regularizing more and more. And we have the same assumptions as before: Hilbert continuity with respect to coefficients, real Hilbert continuity on differentiability, and monotonicity. And we proved the following thing, that if you start with a minimizer, which is in C0 gamma, then the bound improves of an asymptotic like 1 minus gamma. In particular, if you have formally gamma equals to 1, you have no bound because the gradient is bound. So in a sense, we commute Hilbert continuity to gradient integrability. And in fact, we are able to prove that the minimizer is in P plus something. And this also holds in the non-autonomous case. So just let me give you an idea of the proof, because there's an interesting fact here, which is, let me confine to the autonomous case. So there are two ideas of the proof. The first idea of the proof is the following. We want to improve the gradient integrability from P to P tilde, and P tilde is larger than Q, using this Gallardo-Nirenberg inequality, interpolation inequality in fractional Sobolev spaces. So we use the fractional differentiability of the minimizer, and S is less than 1, and the higher and the fractional differentiability of the gradient, and we put the integrability in between. So it's a classical interpolation sandwich. So in other words, if we are able to improve the integrability, the differentiability of the minimizer in P rate but of alpha, then via interpolation, we can improve also the integrability of the gradient. Now, this information comes essentially from the assumption, because we have that U is Hilbert continuous if U is Hilbert continuous, then is in any fractional space. And we want to get this. And let me just recall that we assume that this quantity is finite, which is the Gallardo-Nirenberg norm of U. And this is finite because it is essentially controlled by the Hilbert norm. Because if U is Hilbert, then this makes finite for proper values of these quantities. And then we want to prove that also this quantity is finite. And then interpolation inequality will lead to a better bound, plus other regularization techniques. Now, this is ensured, as I told you, by the Hilbert continuity. So we have to prove that this quantity is finite. So the whole issue is reduced to prove that the gradient is fractionally differentiable, and then interpolation inequality will get the correct asymptotic. Now, how to prove, and this is the first key idea. The second key idea, how to prove the gradient Hilbert continuity. Usually, you get this information by testing the Euler-Lagrange equation. But you can test the Euler-Lagrange equation only by testing with the minimizer. But the minimizer is not in W1Q, it's in W1P. So formally, you have a very weak solution, a so-called very weak solution. So you have to approximate with more regular solutions in order to test. And now there's a problem. You start with a Hilbert continuous solution. You want to construct an approximation of more integrable solutions, but keeping the information of Hilbert continuity. And this is not an information which is kept by maximum principle. First, because you are in the vectorial case, and then you are not requiring that U is bounded by that a certain modulus of continuity is preserved. And here there's the second. So usually, you would do this by making a perturbation with a higher growth functional. So you add an LQ norm, and then you get the minimizers are automatically in W1Q. But this doesn't work because it doesn't preserve the Hilbert continuous information on the approximating minimizer. So what you will do, you will cook up a non-local approximation. So you do not only penalize the LQ integrability, but you penalize the fractional, the Hilbert continuous norm. The Hilbert continuous norm is an L-infinity norm, so it's not good to be treated in terms of integral estimates. So you first approximate the Hilbert continuous norm with fractional Sobolev norms, and then you make a perturbation via non-local functionals, and this is the positive part. So in a way, this is a hook term that sticks this, the minimizer, to keep bound, to be bounded, and this to be Hilbert continuous. What's the drawback? The drawback is that when you do estimates, you will have to combine local and non-local terms. So in other words, we do have the opposite of what is usually done. Usually done is that you get a perturbation of non-local functions with local ones, or you transform in local ones and then you get regularity. For instance, this is the usual approach via Caffarelli-Silvestre. They transform this in a local problem and then they analyze. Here we do the following. We deal with local regularity by non-local approximation. I think that's enough. I bothered you with a lot of stuff, so I can stop here. Thanks a lot.
Okay. Thank you, Rosario. Thank you so much for this beautiful talk. It was really inspiring. Thank you a lot. So now we have Q&A session, and I would like to start by making one small question, if I may. So what happens with the case of problems with the P of X Laplacian? So if I understood correctly, in the case of operators with variable coefficients, those results would still apply and would say that if the oscillation of the exponent is not so big, then you have Lipschitz regularity or something like that.
For the PX Laplacian, you have a different theory. You can do perturbation.
Okay, so it's
You can
not
look at it because
just,
you prescribed that Px is a logarithmic modulus of continuity, because the P of x Laplacian has this feature. Whenever you freeze, you get the P Laplacian,
Mhm.
and therefore this helps a lot. So
I see.
it is still uniformly elliptic enough to allow for perturbation.
I see. I see. I see. So it that those results do not directly apply
No,
to the
they apply, but
but you
these are
need
general results. If you want to, if you stick to the special case, if you stick to the special case, you can do better in that special case. But that is a very special case because it's a model that that whenever you freeze, then you can argue by comparison and not by
I see.
Moses techniques.
But you
This is
still
done in a very old paper of mine for the first time. I think it's 97.
Mhm.
I wrote it down.
But still requires continuity on the exponent.
Absolutely.
Yes. Okay.
There, the difference is the following thing. If you get a minimizer of that and P of x is a logarithmic modulus of continuity, then U is Hilder continuous. And if P of x is Hilder, then du is Hilder.
I see. Very good.
But without this log modulus of continuity, then minimizers can be discontinuous. I think this is the maximal regularity is proven in a very old paper of mine from the end of the 90s.
I see. Excellent. Very good. Excellent. Okay, if we have any further questions, please, the floor is open. I would like to acknowledge that we have a very VIP crowd today. I saw many eminent mathematicians attending your lecture today, Mingione. So if you have questions, please speak up.
May I can ask one thing related to actually this double phase functional. So if A is more regular, say C1 alpha, C2 alpha, can you then get somehow better bounds on the ratio between Q and P? Is it clear?
This is a good question. I sometimes wondered about it. I don't know actually, but okay, because you see, because you see the example, right? That tells you that that the more regular, that you require more distance between alpha and this, and we thought a bit about that, but I don't remember. We made some computations, but it's something definitely worth investigating.
Okay, thank you.
Thank you.
Any other question?
There was a question earlier in the chat. Someone asked, please give an example of F, where F is an element of Ln1.
Here it is. It was at the very beginning. Log. Essentially, if you take 1 over x and you drop the log, then this is in Marcinkiewicz, Ln-Wick. Then if you start adding logs, then you go better and better from Ln-Wick until you get ln, then becomes really ln, and then you can go better and better. I mean, the second index goes in the other way, in the opposite direction of the first one. But essentially, the second index makes the logs appear.
Okay, it seems that we don't have any further questions, Mingione. So please welcome. Let's thank Rosario once again, and I'll pass the floor to Stan.
Thanks very much for the very interesting talk, and thank you, Eduardo. Thanks for coming, everyone. And yeah, next week we have Muhammad Mustafa Fall about constant non-local mean curvature surfaces.